I'm Scott Peterson. I work for Intel in Hillsboro in the data center group. Lately been working on improving the performance of Ceph when deployed on rack scale design type clusters. Everyone has seen at least one slide about Ceph, maybe even today. So the thing to clarify here is we're talking about block, and you probably know that Ceph is basically an object store. Everything is is really objects. We are talking about RBD. That's the block interface, and specifically we're talking about the user mode librbd. There's a kernel mode librbd, but we're not touching that. So in this complicated picture off to the right, because we can't explain Ceph in 20 seconds, is to illustrate that it's pretty complicated. It has a lot of stuff to do to make sure that your data is everywhere it needs to be and nowhere it's not supposed to be. And the thing to keep in mind is that's not free. So the Ceph OSD nodes are a lot of times constrained by CPU, especially when they have SSDs they're using for OSDs. So just said most of this. The replication is controlled per pool in Ceph, not per OSD. You can subdivide your OSDs into groups based on geography or whatever. And those properties are all per pool. So the default, if you just deploy a Ceph cluster, use Ceph deploy and spin one up, there'll only be one. Actually, I don't think there'd be any. But when you make a default one, basically all the objects are spread over all the OSDs everywhere. So that's something to keep in mind about your RBD volumes, that RBD volumes are split up into 4 megabyte objects by default. They can be smaller or larger, but you have to specify that. And there's a pretty good chance that they're on every OSD everywhere. So you don't configure RAID per volume in RBD. You put it in the pool that has the right replication property that you wanted. And this decomposition of volumes into objects is the basis for all the snapshotting and thin provisioning that Ceph can do for you. So you'll create a volume. Initially, it'll have no objects in it, and as you write to it, it'll populate some. You decide to make a snapshot of that. That's basically pushed down the stack, and another empty image is stacked on top of it. So that's important later because we can exploit that for the shared read cache. So this splitting it across a bunch of objects has a lot of performance implications. Many of them are good. You've got a lot of devices, so you'd think that would make it faster. If you care about completion latency, this means you have a lot of chances to be late, basically. If any of these things is unhealthy or unhappy for some reason, it's going to be slow, and since your volume is probably everywhere, your volume will probably be slow. Sometimes, inevitably when that matters. So Intel's doing a number of things in the caching space. I mentioned the shared RO cache. Yuan is sitting right back here. This is his project. And this exploits the fact that in that stack of snapshots in Ceph, once an object is in an image that's not on top anymore, it can't change. Yeah, there's still RADOS objects and they're still writable, but librbd won't touch them anymore. And that makes them very cache friendly. So the shared RO cache makes local copies of those immutable things in SSDs. So if you've got a lot of, say, clone volumes in a VDI instance or something, then they have a common parent. Then they can all exploit the same cache. So the shared RO cache uses what RBD calls the object dispatch interface, which is near the bottom of the library. It's by the time the library's figured out which object your LBA maps to, this is where it dispatches the I/O, and it's got a stack of things it goes through, and the local cache is one of those things. The write-back cache, which is what the rest of this presentation is about, is what I'm working on, and it basically we're using persistent memory to complete your writes locally, and then we promise to flush them later. This uses the image cache interface, which is at the top of librbd very soon after the writes come into the library. librbd, by the way, the entire thing is all C++, which I found a little shocking. So, how many malloc calls do you think there are per write in RBD? 11. How many do you want? None. But This is not the biggest problem. So it actually performs pretty well. It's part of the reason that there's all these cores are really busy. So the sort of third tier of this is the replicated write-back cache, which happily is virtually identical to the write-back cache. In fact, the data path is the same. It just needs a control plane to steer where the replicas go, which we can't build yet because, well, I'll go into that later. But there's some pieces missing. So this is sort of the, okay. This is probably the fifth slide you've seen about persistent memory today. But the thing to highlight is that somebody decided it was a good idea to call two different things Optane DC. But they're not really the same thing. So there's Optane DC persistent memory, and that's what we're talking about here. Apparently, there's Optane DC SSDs, but you can't RDMA to those or map them or directly address them with instructions. So we're not interested in those. So this is the things that everybody loves about persistent memory, and that's what we're exploiting here. The remote part is actually this was the real factor for us. That if when we're replicating to a remote persistent memory pool, that's a hardware write path. Remember, a Ceph OSD node will be CPU limited. So if you propose to the Ceph community, I know I'm going to have another daemon on your OSD that's going to handle replication of these writes, it's a non-starter. So as Andy mentioned, FSDAX is not quite here yet. But despite that, this is designed to use FSDAX. Upstreaming a patch to Ceph, just like the kernel, takes a while. So this patch is actually in review now, and if everything goes well, it'll be part of Mimic, which comes out at the end of the year. And FSDAX probably isn't going to be actually. I'm not exactly sure when FSDAX is going to work, but that'll probably be before the next Ceph release. So doing these things in advance is kind of required. So I'm a consumer of the PMDK and the persistent memory stuff, so I'm not here to tell you about how it works inside. I've peeked inside and I know a little bit, but the guys that actually built it are around, walking around, you can ask them. So this is kind of an example of an application for persistent memory. There aren't very many. So as an experience of developing this, it's it's simpler than using files to persist your stuff. It's almost as simple as just making objects in memory, but not quite. There's all these the visibility. This is the PMDK presentations went over this in great detail. But whether you're using files or persistent memory, you still have to think about that, right? Like what changes to this persisted data? What's the visibility, granularity? When do I need to make sure that it's actually readable again if I crash? That kind of thing. You have to think about that still. One of the key gotchas here, which is weird when you think about using malloc versus this. You can allocate a thing and then patch up the object that points to it later, and that's okay, because if this process crashes, everything goes away. But not in persistent memory. If you allocated it and didn't have a pointer to it, you'll never find it again. It's just gone. So PMDK helps you with this by A, the transactions, and B, the splitting memory allocation into reserve and publish. So you can reserve a piece of memory, you can know where it is, you can write to it, you can even guarantee it's persistent, but it's not actually allocated until you publish the allocation. And so we exploit that here. This is so persistent memory is kind of overkill for a RBD write-back cache. So you might wonder why we do this, not an SSD. But caching is always metadata intensive, right? Every write has a little bit of information that comes with it that you have to keep track of. If you put this on a block device, you've got a lot of tiny writes, and no block devices are happy about that. That's one reason. The PMDK support for transactions and allocation is another big reason. That's not necessarily motivator for everyone, but the sort of unique situation we're in here with the write-back cache patch to Ceph is when going upstream, you have to make your case to the community. You have to submit a patch that's consistent and it works, and it's small enough that they can understand it. You don't want to touch multiple subsystems, and so this kind of thing, like the support for allocators and transactions in the transparent replication, it really simplified this write-back cache. The logic for it is actually pretty small. And in fact, the Ceph people were ecstatic about the fact that they were trying to talk us out of doing replication. They did not want that complexity in that library, and for good reason. It's kind of gnarly. If it was implemented right there in the RBD code, it would be prone to breakage. So the fact that pool replication means that the data path for persisting locally and the data path for persisting to a replicated pool is the same code, that was very popular with them. It also made it smaller. And of course, like I said before, the hardware write path, that was crucial for some of this stuff. So here are all the moving parts. Like I said, we are talking about this is dead. No, it's not. Yes, it is. Okay, well, whatever. We expect your application will be a hypervisor. That's the main application for librbd. It's QEMU. So inside librbd, there's that ugly green box. This is the automatic color selection for PowerPoint. I don't know why. We logically have those parts. The replicator, since we're using pool replication, is pretty thin. But this design, when we started this project, we weren't sure we were going to be able to use pool replication. So we thought we might actually have to implement replication in there. So at the very least, the replicator box that represents the source of writes and the master. PMDK has this notion of the master pool in a replicated pool, and that's the only thing that can write. Everybody else is just passive. And the write log is the data structure and the logic for laying it out. And the flusher that's yellow there is the thing that writes it back to RADOS, basically to librbd. And if you have a replica node, then those gray boxes are that gray flusher. That someday, if you die, will light up and be the thing that flushes your writes out to RBD, and that's how we guarantee that writing happens. The other way we guarantee writing happens is if you crash but come back, then it's persistent. So there they are. When you open that volume again, we flush them out. So we could actually flush from the replica. Sometimes it would make sense for us to flush from the replica node, because in a Ceph cluster, the OSD nodes tend to be on dual networks, so they can do all their internal traffic on a separate network from the payload from the applications. And so we talked to the PMDK people about making the replicas readable, and they could probably do that at some point. But for now, in RWL, the flushing will always happen in the client, and it won't happen in the replica node unless the client has died. Let's see. So the other important note here is that we're using, as we said before, we're using FSDAX. And what that really means is that in this pmem box, that's an NVDIM with an FSDAX file system in it. And each RBD volume that's open on that client node in the top box has a file for it, basically a pool file in that NVDIM or pmem pool. So it's laid out like this. I was going to have a slide that talked about the size of the cache and the things you have to do with larger or smaller caches. So one of the things we had in mind, because I come from a world where we did HA write-back caches that were large enough to hold the entire volume if you wanted it to. We wanted this thing to be able to get large enough that you could have, you could sustain high IOPS to an RBD volume, maybe indefinitely. But of course, that has to be very large, and you have to be able to free space in the cache. So this sort of buffer allocation mechanism that we do here, there's a ring like you'd expect for a write log, but the data buffer, the data doesn't follow the entry in the log. The data is someplace else that we allocate with the pmem APIs. This does make for a lot of pointers. The real reason I did this is so that they can be separately freed, so for instance here, LBA 16 is written to twice, once at the top of the list and once at the bottom, and so we could, if we're doing optimized flushing, then we never need that first write ever again. So we can free that, we can have that space back. The other thing it lets us do is parallelize. You have writes coming in from multiple threads. You can copy and persist the payload data, which maybe it's Maybe it's in memory that's paged in, maybe it's not. You don't know. It came from an application, right? You don't know what you're going to have to do to write that and persist it. And those things can all continue independently. And only when that's done do you finally have to append the log entry. So that's the only time that you care about the order. If these things are happening at the same time, you just let them race. And then we do finally have to decide on an order before we complete them. So there's the basic flow of a write. Comes into the AIO write interface in librbd. We keep overlapping writes from being in flight at the same time. Remember that replicator box? And I said that might be more complicated if we couldn't use pool replication. This is the main reason for that, because if we weren't using pool replication, then we really need to make sure that there aren't overlapping writes in flight at the same time, because they might bind in the opposite order at the other end, and that's a disaster. The other sort of side benefit is that it helps us keep track of what we can safely flush in parallel, because that was the unexpected thing that happened here was, which shouldn't have been hard to guess, but you take whatever your queue depth is and you run it through a cache that writes back and doesn't know what the parallelism was, it turns it into queue depth 1. So flushing sucks unless you can get some kind of clue about what was concurrent. And this helps with that, but there's these other things. Okay, so like I said, we split allocation into reserve and publish. So the first thing we do when we get your write is we reserve a data buffer, we copy your data into that address space in persistent memory and persist it. And the way that API works, when you persist in a replicated pool, it also does the RDMA replication. So that call will actually wait for an RDMA write to happen and then the trailing read that they do, because PMOF is not a thing yet. And then, so you wait for that to complete. And so there's you got to decide, do I want to do that on the caller's thread or do I want to punt that to another thread? And there's reasons, sometimes it's a win, sometimes it's not. So most of those details I'm leaving it, but there's a couple of places like that here. And then we schedule the append operation, and this is the only time that we actually guarantee any order. Once we decide what order they're gonna appear in, this is the first time that they actually have to acquire any kind of, unless they overlapped, that they have to contend for anything and wait for each other. And then the transaction magic in PMDK lets us, atomically move the ring head pointer and publish their buffers, and then when that's done, ta-da, you're visible. We also make them readable. So probably obvious, but a write back cache, you might get a read for a write you haven't flushed yet, and if you get that, you have to satisfy it from the write back cache. So there's actually a fair amount of the complexity of this. Since PMDK hides all the replication for us, a fair amount of the remaining complexity was making sure that we can look at an incoming read and split out the hits and the misses from the write back cache and send the rest down, and then satisfy them going up. The read path is obviously really short. It's a mem copy, because it's all still sitting there in our address space. And then we finally schedule completion for the appended entries back to the caller. Now there's a question. Yeah. Okay. So our librbd has this notion of persist on write or persist on flush, and usually it does this automatically for you. If you ever tell it AIO flush, then it assumes that you are willing to defer the persistence guarantee until that flush, and then we'll start completing your writes as soon as we can, and then we'll only defer completion of the flush for all the writes that led up to it. And this is kind of interesting. Andy and company touched on the issue of failure of an NVDIM causing a machine check. So that's bad, obviously, but if you're implementing a write-back cache, that's actually kind of handy, because that means that as soon as you're done with that user's buffer, you can complete that write, because if this device fails, you won't be the one handling this failure. So the replica will handle it, because you're done. So we don't do that, because you could cause a machine check, but it's not actually guaranteed to happen. And they'll fix this in the platform eventually. And, there's no way to guarantee it's going to be fatal. So all right, so the bad things that can happen, pretty short list. I mean, yes, lots more bad things can happen, but the main ones we're worried about is your node dies. Well, if your node dies and comes back, the write log is persistent, so we finish all the writes that we completed to you. The The transaction mechanism and the publish reserve mechanism that we use mean that if the writes didn't complete through the append phase that we outlined a couple slides ago, then it's as if they didn't happen. So when you open this pool back up again, things may be laying around in there, but the ring pointer didn't get advanced and the allocation didn't happen, so those writes are erased from history. Right. Okay. So if the replica fails, this is the easy case, you make a new replica. So there's really nothing special about either of those cases. You can, from the point of view of the application, it's just gone. It's somebody else's job to make it come back, and there's nothing really to do there. I keep saying this, PMDK pool replication is experimental. That's a thing that I should point out. It is. So it works great, but it's not actually a real boy yet. So one of the things about it is you can open and create a pool trivially. You can't open and create a pool set trivially. You have to create that file yourself. And if that was configured with replication, there's no way to change that on the fly. You actually have to close it and then use the pmem pool tool to change the replication properties. That's a little awkward for a volume that's open and has its write-back cache there. So that's one of the reasons that we're not. Replication isn't this patch that's going up now is the local unreplicated case, which I guess I didn't explain. The Ceph people are fond of this notion of crash consistent write-back, which means all your flushes happen in the same order, which is really inconvenient if you have a large write-back cache and you'd like to optimize that. But they like it because your file system is never corrupt in theory. If you lose 10 seconds or a minute's worth of writes, it's still a good file system. And that's true, but the CSPs that use this stuff, they don't use any of those write-back caches because that's not good enough for them. They have an application that said this write completed, and then that machine dies, and the write didn't complete after all. So, right. Oh, we discovered this is the one I mentioned earlier. So, right. So because we can't really can't guarantee that we'll die if the NVDIM dies, and actually we don't want to. In the glorious future, we'll be able to survive this. Then you got one of two choices. Either you paid for another local replica, and you can write it out by using the local pool replication that one of the other PMDK guys talked about, but that costs more. We expect people won't want to do that, so we will need to. We expect we're going to have to do is basically flush the remote cache and then continue in a degraded state until you want to migrate this VM someplace that has a working piece of PMEM. Or if there's a second DIM, if you didn't want to do mirroring, you may still have a local DIM and you could resilver to there. But it's nothing magic about this. But from the point of view, wanted to highlight again from the way this write-back cache is implemented in Ceph, there's once there's an API for PMDK to control this replication configuration, the data path doesn't really have to handle any of this stuff. There's no special cases for this. Your write or your persist operation either succeeded or it didn't. And if it didn't, you go fix the pool and try it again. So let's see. All right, so what we're after here, like we said, there's a continuum of cache sizes. You can do different things with small caches than you can with large caches. With a small cache, about all you can do is be a capacitor for writes so that your latency is predictable, and we are able to do that. We want to get to the point where a large cache can actually either enable high IOPS or shield the cluster from a lot of that I/O. That's another way to get cluster capacity is don't send I/O to your cluster. Well, if you can satisfy it in the cache, and then a lot of it is rewritten or discarded for a long-running VM, well, that's a win. The problem with large caches is they take a long time to flush. They take a long time to replicate if something fails. And the RBD API, its operations like snapshot are synchronous. And you have to flush the cache before you can create the snapshot. And if it's going to take 5 minutes to flush the cache, then it takes 5 minutes to make a snapshot. That probably means your VM file system was frozen for 5 minutes, and that's a non-starter. So this all boils back to, in the current state of RBD that exists now, large caches just aren't viable. There's no way to manage them. It's intrusive into. Now we hope we can fix that. But first we have to deliver a cache that works for them, that actually solves the problem. So we chose this sort of VM use case of modest I/O rate of everybody's favorite write size with a reasonable queue depth, and we said, what if we can get 4 nines under 3 milliseconds? Well, that would mean that you could do several writes and have some chance of completing a transaction basically in a reasonable amount of time. 4 nines was probably, I just picked that number out of the air, and it was a really bad idea to pick that number, but it's stuck in all the requirements. So here we are. Right, we used some hardware to do this. We have a little toy Ceph cluster. It has 3 nodes, 12 OSDs, and the client is a separate machine, and everything's on a 25 gig network. If you wanted to try this at home, I had to use a version of FIO that actually calls RBD IO flush, because you can tell it to put a barrier every n writes, but if you're using the RBD backend from the normal version of FIO that we all have, it never actually calls flush. So this version does. And because, recall, FSDAX isn't a real thing yet, so that means that PMDK, being conservative, is going to make a syscall on every persist call, or almost every persist call, to guarantee that it's really, really safe. So we're targeting a world where FSDAX works. So we override that with this environment variable that says, trust me, it works. And so it doesn't do that anymore. We're using a 1 gig cache, but that's really a lot larger than it needs to be. There are, down here at the small end of pools, it's getting smaller than that. It's actually inconvenient for the PMDK memory allocator. It really likes to work with more space. It likes to have arenas allocated per thread. If you have an application like a hypervisor that has hundreds of threads and they each have their own arena, well, there aren't that many arenas to go around. So you end up running out of memory for when you actually have memory. So we make it bigger so that we don't hit that problem. This actually may mean that we have to stop using the memory allocator and having separately allocated buffer. Because the other thing is that when you have a small cache, those separate buffers, it's not big enough for us to ever see a discard or see an overwrite. It's not going to happen for a tiny cache. So really we need a different allocation mechanism for the small caches and reserve that separate allocation thing for the big case. I didn't want to have 2 data paths, so this is the one I built. So this is what we got. So the first column here, we have a single 100 gig volume, and that workload we described earlier, we're capping it at 2K. You can see that Ceph, without any help, 4 nines is up in the multi-tens of milliseconds, and we got below 3 milliseconds. And even if you didn't care about 4 nines, at 3 nines, you're still getting a significant improvement. The other column, we did 16 volumes, which were only 10 gig. Actually, that was a mistake, but my test scripts, they were designed to run on a cluster that was a lot smaller, didn't have as much space. I didn't have room for 1,700 gig volumes, but this cluster did. But anyway, so those volumes are smaller. It doesn't make a big difference because, like I say, the caches aren't big enough for there to be any overwrites, and we're using ordered write back flush, so we're not eliding anything anyway. So you got similar results. So we hit this goal. So this means that with this patch, you can, if you want to have VMs backed by RBD, and you want to be able to do multi-write transactions in a reasonable amount of time, this actually fixes it. It makes that possible with a very small amount of persistent memory. So like I said, these pools are a gig. If I fix that allocator, they can probably be a quarter of that or less, which means that if you had a hypervisor with hundreds of VMs, you'd have enough room for one of those for all of its volumes, basically, and you only have to pay for 1 DIM. Which is the biggest feedback we got from talking to these Ceph users is, yeah, but I don't want to pay for persistent memory. Okay. The other feedback we got was, I want it to work on an SSD, but we can't replicate in hardware to an SSD, so We're going to make it work on an SSD anyway for the local case because the community wants it, and it's important. Like I said, there's these two interfaces for caching, and if nothing is using them, so if the community doesn't use this cache because it doesn't do what they want because they have to buy persistent memory, well, then the interface will sort of decay away. It won't be maintained anymore, and then it won't be there when FSDAX shows up and the price points shift, or there's a great use case for a larger write-back cache. So in order to keep this alive and used and maintained, it's in our interest to make it work on SSDs, even if we don't get to sell any persistent memory doing that. Okay, so you have to have a call to action slide, I'm told. I didn't really want one, but here we are. So we can get there. We can take your 20 millisecond tail latency down to 3 milliseconds. It'll basically use 0 CPU on the replica side. In our lab, when we used there was a kernel version where this pool replication worked at least to the fake pmem. But with all the thrash with this FSDAX fix, at some point that stopped working, that's the state we're in now where FSDAX doesn't work. You can't register that memory because you'll get this can't map user pages error out of your RNIC. But there was a window where it worked, and it probably meant that it was unsafe the way it worked. But the data path worked, and we could see that the overhead for the RDMA part of the RDMA replication, you could measure it, but it was way less than the latency we were trying to mask in Ceph. So that's promising. When we get all these, when the features appear, we're pretty sure this will actually come together. So this patch is in review now. You could look at the code if you wanted to see how you do storage applications using persistent memory. You could make that replication work. You'd have to build a kernel that had the buggy FSDAX patches removed, and it would be this big science experiment. You probably don't want to do it. But the code is there. And you can use it now without replication. But again, part of FSDAX is that map sync. You don't have map sync either. So PMDK is going to be conservative, and it's not going to perform like this until 4.18-ish when that's fixed. So you could try it, you could review it, you could let us know how you would use this. That is that. Any questions?
You only need 1 gigabyte of the pmem for RBD.
Per volume. Yeah.
Small size compared to the NVMe fabric. Did you find any optimal ratios between the pmem size to again?
Well, so we're not. So I'm benchmarking this with FIO, right, which is not like any application that ever really happens. So if you had a bursty workload and you could characterize that, then yeah, there might be sizes that would make more sense for you. But no matter what you do, if your workload is writing at a higher average write rate than your Ceph cluster can sustain, then your cache will just fill up. How long will that take? Well, it depends on a lot of things. It's really hard to predict what the performance of a Ceph cluster will be. You have to basically measure it, and you have to know what else is going on there too. So it would be a case-by-case thing. There might be some rule of thumb for certain classes of applications, but in general, no. Right. All we're trying to do is fix the latency, though. So we really don't need a lot of space. Yeah, that was on the slide here. Right, yeah, average, right. So Ceph gets 2.2, we get 165 microseconds. So, even that's kind of embarrassing, right? This is memory, so we shouldn't be faster than that. But remember, this is a C++ thing. We're still switching context at least twice to get in and out of librrbd. So that's the other thing. So, you can do better than this with applications using frameworks like DPDK and SPDK, but those are completely unwelcome in this user mode library. This is a library that any application can link to. It runs as any user. So for example, like the work queue mechanism in here, the Ceph work queue, the thread pool mechanism that lives under their work queues, doesn't even have a way to specify the priority of the threads because you're running as any user. You might not have permission to elevate the thread priority. So that was the first thing I looked at trying to do because in a previous life, in the Dell caching product I worked on, just having some threads a couple notches above other threads made a huge difference in terms of them getting preferential treatment and completing the critical things quickly. We didn't do anything special about mapping traffic classes to cores or anything like that. We certainly didn't pin to cores because that's another privileged operation. You can't do that in the user mode library. I mean, you might be able to, but you can't count on it. So, I should have said that node, that client node was unloaded, which you can imagine since these are user threads at some random priority that a lot of other activity would have affected this performance. So the next thing to do might be to test it in QEMU and see what it does with its worker threads that handle virdIO block and make the librbd calls. And if they're, I didn't do that mostly because that's a big cumbersome test setup. And every time I change the library, I have to change the hypervisor configuration. It slows everything down. But we could also propose to the librbd guys in the Ceph community that maybe your thread pool ought to have a priority mechanism. So, anything else? The flusher still runs in, just like the flusher still runs in the context of the application. So, I mean, back in this picture, where was it? Right. Sure. Oh, no, so we called this the replica daemon. This box here is this, what we're gonna end up creating is another daemon that will start up in the OSD nodes, which will listen for connections from librbd instances. So, and the reason we want the replicas to be in OSD nodes in Ceph is they are actually full members of the Ceph cluster. They're monitored. You have some idea of whether they're up or down, and whether if they're down, are they coming back? You know that. Client nodes, you don't know that. So, I mean, one of the first questions people ask is, why don't you replicate to another client? Why are you bothering even to send it into the Ceph cluster? Well, client nodes come and go at will. We can't predict when they're going to be here or not. And so if we're trying to guarantee that we're going to flush your writes, we have to have at least one replica someplace we can control. So right.
Now, why not put the primary cache also on some OSD node as well?
Because then we can't access it locally. With you lose all that. It's not mapped into your address space. It's not. You can't use the. The PMDK APIs for persistence assume that you can address it directly. So, pmem, for instance. You have to have a local mirror in RAM of the pool you're talking about remotely. So actually, when I started this, pmem wasn't a thing. That was buried inside pmem obj. So you could make that work, but I think that whole thing has to be pinned for RDMA. So yeah, it also would slow, yeah. Yeah, so it's kind of want to constrain the number of cases that we have to support here. So the large cache case would be kind of a problem if both copies were remote, right? So you'd have to dedicate a huge amount of RAM locally to manipulate that remote copy. So, and in the large cache case, read hits there should be a lot more read hits, right? Because if you're running for days, and say you're a database and you're modifying the same stuff over and over and over again, you're also reading that stuff, and the most recent copy is going to be the one you have written that has either, maybe it's been flushed, maybe it hasn't, but it's probably still in the write-back cache. And if that's remote, then that's not free to do anymore. So.
Just one more thing for remote, right? So you're saying basically the remote pmem, the replica on the local cache. Does that mean, and that also on the OSD node, does that mean that on each OSD node, they need to have a pmem cache for every single client?
No, so the straw man is that when you open an RBD volume and you want replication, we'll choose an OSD node to be the home of its replica. And there's a pretty straight, what we proposed to do was choose the OSD node that has the first object for the volume. Look there first. If it's got persistent memory and it's got free space, then make the replica there.
Sure, but I have two different clients on two different nodes, right? They are accessing the same OSD node. And so basically they have their own local pmem pool.
Right.
And their own local cache. And then on the remote side, I need to have basically two different pmem pool as a remote replica for the two different local pools, right?
Right. Every open volume, every open RBD volume with this scheme has to have a pmem, a pool, a file in a pmem file system on the client, and another one on some other OSD node somewhere.
Even though the same wouldn't get opened by the two different clients.
Oh, that doesn't work. This is not coherent. You can't do shared access. So none of the write-back caches do that. We know how to do that, but it's really hard and really complicated, and we're not going to.
I don't know about Ceph. I know VMware is a lot more multi-writer. You can open that from Peterson.
Which? NVMe?
No, ESX.
Well,
ESX, you can open
yeah, that's kind of a special. Yeah, right. They can do that. I don't know how their caching works, but yeah. So there's a special case I didn't really have time to go into here, but we don't expect to make a coherent shared access, but it might be sort of required to do VM migration. I think if you look closer at that, it's not actually required. What's required is something that looks like shared access, but is really coherent. You need to make the reader needs to see a coherent view, and then the source of writes moves at once and doesn't move back, is what I'm pretty sure happens. So we think we have a workaround for that, which is imagine another client node, which is where your VM is moving, and so we will, because this would require integration into the hypervisor because this is not part of the librbd interface. So now suddenly this isn't a Ceph thing anymore, it's an OpenStack thing. We would need to spin up another replica on the machine it's going to. Once that's up, then we need to, if we were doing persist on flush, we need to stop doing that, and we need to do persist on write for everybody. And that means all replicas are consistent everywhere. We also need readable replicas. That was the other reason we were asking the PMDK for readable replicas. So now, once you've got that, and all writes are persistent everywhere and readable everywhere, that means that hypervisor on the other end can start warming up those pages from storage like it likes to do. And then, in theory, the first time you see a write at the other replica, we tell RBD, we're moving the writer now, and then this replicator roll, that one goes gray and this one goes green. We tell PMDK, this one's the master, and now writes come from here, we hope, and we hope they never go back. But if they go back, then we have to slow everything down and bounce it back in. Hopefully that doesn't happen, but we haven't built it yet, so we don't know. And then that guy closes it and that replica goes away. That's the plan. But since we don't have a control plane for replication yet, we can't actually try that. But coherent is hard, and that's what I've done in previous lives, and a lot of applications just don't care. So, I mean, maybe there's some distributed databases that want that, and they're just not going to be able to use this. All right, then, we're finished.